Good afternoon. Can you hear me?
Yes.
Yes, ma'am.
Thank you.
I think your extension really works. Yeah, I just finished the presentation this morning.
Yeah, I understand. I understand. It's getting very busy, I'm sure.
Right.
That's okay. You know, with me, the most important thing is that you do the work. I mean, the deadlines are, of course, are important, but learning is more important for me right now. So within reason, obviously, I don't mind extending a deadline. So.
And our second wave of capstone presentation starts from October the 19th.
Oh, they have presentations?
Yeah, this semester we have 3 presentations on capstone.
As opposed to what did you have the previous, do you know what was happening the previous semesters?
I don't know.
It was the same.
I was about the same. Yeah, I know it's heavy. I mean, usually it's a lot of work in those projects.
Yeah, the deadline for, yeah, and then starting from November the 9th, that's the third wave, the final wave of presentations. The deadline for final report and demo is November the 24th, the day before.
I know. It's all squeezed this year.
Yeah.
You know, we started like maybe a week early, but we are.
Squeezed. It's just the 3 days moved forward.
I don't know. I always thought that we were getting early in December. Yeah.
Yeah, and we started 3 days early as well.
Yeah. Yeah.
So
it feels though very crunched, the whole thing. But you know, I think it was a good idea to try to finish before November instead of having the students move back and forth between their homes and the campus.
Yeah,
you know,
so
this time.
Yeah, the students having home in the US may get back, I mean,
right,
during the Thanksgiving.
True.
And it does not need to come back again.
Yes, that's true. Yep. Well, we have 2 more minutes before we start. In terms of the exercise today, I will create one right before around 3, and it's going to be a simple exercise, conceptual, on what we're gonna discuss today, and then it's going to stay open until 9. Good. So that's what we're going to do. So we don't take, because the lecture is already short, we don't want to take time. I also wanted to say that I've looked, even if the deadline is, I believe, today for the survey, I got some very good comments and feedback, and I truly appreciate those who provided that. And I do understand the issues in relation to new concepts and trying to rush through a review about previous concepts and so forth. And the need to spend a little more on the approach how to do homework. So what I plan to do moving forward is this week, I will try through exercises to help you integrate the concepts that we've learned so far. And as a matter of fact, I will, when I get all of the comments, I will try to put them together and then present to you what were the most important points that I got out of that. I think you can also see the results yourself to some degree. Is that true? Because I noted there that they should become available, but maybe after the deadline, you're going to see them. And then, but the comments, the open-end comments were very important in terms of suggestions. So I'm going to present those to you sometime on Wednesday. We'll try to put them together. I don't want to take the whole hour going into the weeds, but the most important points. However, what I do understand is that we got a very, which is, you know, in a project like that, in a class like that, you really get into advanced concepts, and then you need a lot of information from the previous classes. And I wanted to say that this week we are going to we are going to be modest in introducing filters, which we were supposed to do, but I wanted to spend time like Monday and Wednesday trying to integrate the concepts we had, but also doing that while we focus on real applications, because this is going to help you in your project too. But I wanted to remind you that what we did in this class was like start with transmission lines. So transmission lines and matching networks are extremely important, as you will see. Very important because they help you practically design a receiver. If there is anything fundamental in a receiver design, I will say these two get the top rank in terms of how fundamental they are. Then we talked about network theory. And the network theory is very important too, because of the following. It provides a language for us to talk about the pieces of the receiver. The one thing also I wanted to remind you is that as you go more and more into real systems, you lose the depth that you had developed in the individual pieces. So for example, you've learned a lot about transmission lines, about circuits, RLC circuits in the early classes. We learned in 322 about transmission lines and matching. Then you learned about, in other classes, about active devices. But you learned about resonances in time domain and the frequency domain. And then we covered, in fact, part of this resonant RLC, just as a review of the RLC circuits, but you've learned about those. And as a matter of fact, probably you did a lot of problems around them. But as now we are moving into the system, into the system area, then only a few pieces, you don't need to look too much into depth in any one of them. There will be a few very fundamental things you will need to take with you and use those to be able to make the receiver. You will assume that the individual details have been already worked out. all right, somehow, and they have become available to us. So when we talked about transmission lines and matching, we did not necessarily say a lot about how to find the characteristic impedance of a realistic transmission line. So we talked about microstrips here. We talked about the microstrip. We talked a little bit about the CPW, not because we are going to use CPW, but because it's a very popular transmission line, and I want you at least to have heard about it. We are going to primarily utilize microstrip as the base transmission line. We talked about matching. We talked about also how to calculate and use some formulas that will give you the characteristic impedance of a microstrip, but not necessarily we did not derive them. And we're not interested in deriving them at this point. We just want to get the formulas that have already been derived using fundamentals and use those. In the matching, we talked about realizing matching circuits in microstrip form, but of course, we used formulas, all right, that were available. Now, we made a pause at that point and talked about network theory. And why is it that we talked about network theory? Because a lot of the things that we learned in transmission line theory and in matching, as we move up the ladder and we are looking into systems, we are going to use for passive components ABC matrices to talk about the passive parts. All right, so you saw a little bit about this when we talked last time in brief about the receivers. And then also we said that later we're going to talk about noise in more detail. And we talked about how networks are cascaded because that's how you do a system. All right, so in a complex system, you're going to split it into small pieces. And then you're going to try to connect these smaller components. And usually, if it's all passive, you use the ABCD matrix to do that, because primarily this is the best way to connect the gain of all of those. All right, so the gain of one times the gain of the other times the gain of the third really gives you the gain of the whole cascade. So ABCD matrices, for each one of those, if we find them, then we can multiply them. All right, these are in passives. So network theory, what it does is to take us from the details up one level. And within the ABCD matrices, we hide a lot of those details, which can really confuse us tremendously when we try to do systems. So in systems, abstraction is extremely important. Otherwise, you cannot develop a complete system. So network theory allows you to do this abstraction. And what did we learn in network theory? We learned, of course, about ABCD, but also we learned about scattering matrices. All right. And we learned about other matrices, Z, Y, and so forth. All of these help in some ways. Now, after that, that was important to introduce, we went back after we introduced network theory, and then we tried to talk a little bit about resonators again. And resonators, RLC, is a good thing to review. Why? Because anything you do in using sections of lines or using inductors and capacitors eventually will resonate. Sometimes you don't want to have a capacitor in a circuit, but the capacitor presents itself because of parasitics. And so we did the resonator so we understand what happens when a circuit resonates. We started with RLC, and then as we will go down, you will see that any matching network will resonate, all right? And will resonate, is gonna have the best performance at the design frequency where you wanna be. But somehow later, at some point, at resonance, that system is gonna change its performance substantially. When you have an LC, so it's the most fundamental resonator, what happens at resonance? If below resonance looks like a C, above resonance is gonna look like an L. If below resonance it looks like an L, above resonance is gonna look like a C. And so you have to stay away from these resonant frequencies to be able in your matching network to have a true representation of capacitances or inductances wherever you want to have them. Otherwise, if you hit the resonance of any of those, then practically your matching network has been destroyed. So we talked about resonators. And then when, of course, you go to resonator, how do you talk about resonance? The resonant frequency omega naught. You talk about the bandwidth, which is in fact the place that you define around the resonant frequency. And we defined it now in terms of the input impedance, if you remember. And there is a series and there is a parallel resonance, fundamentally, these two. But then also we define the Q, and the Q is 1 over bandwidth. So these are the fundamental concepts about resonators. Now that we have the network theory in place, we have, remember the resonators, we introduced bandwidth and Q. We have the transmission lines and the matching circuits. Now we have enough in our toolbox to start thinking about something higher, of higher complexity, and of always thinking about components in our receiver. And that's why it was important to introduce the receiver concepts early. So you have a sense of why we are looking at filters, as we will do next. Why are we looking at amplifiers? Why are we looking at mixers? If we did not have an introduction to those systems, then I will go from one to another, and you will think that like you will have no understanding of why those three are so important. So of course, filters, amplifiers, mixers. Now, these are fundamental. Without any of the three, you will not be able to do a receiver. Now, are those three the only ones that are required? Of course not. You will have local oscillators as a second level, but I will assume that the local oscillator can be any other generator. Of course, you're going to have the matching networks, which are embedded up here. All right. So how are you going to connect one to the other? Through matching networks. Okay. And then, of course, as I said, you have the LO, you will have, which we are not going to cover in this class, you will have the analog to digital converters, you're going to have digital to analog converters, you may have couplers, you may have all kinds of different things, which we are not going to cover in this class, because of course they are important. We'll assume that this is LO is going to be given to us. And everything else, of course, they are important for a system, but this is not part of what we're going to do. Okay, so we have not yet touched filters, amplifiers, or mixers, but without having the information that we have got so far, we cannot just talk about these three groups of components. The other thing that we spoke, and we did it through homework, was to talk about passives, okay? And passives Usually when people talk about passives in circuit design, what they mean first of all, resistors, inductors, capacitors, all right, number one. And then at the higher level, of course, matching networks. Now, what we've seen is that now, even through our homework, that both inductors and capacitors, they're not like the LNCs of the low frequency applications that we've seen there as fixed components. The passives in high frequencies, because they are made out of three-dimensional geometries, have resonances. So both resistors, we did not do the resistors, we'll find a way to do them later. An example for it. Both resistors, inductors, and capacitors, as you have seen, they have a lot of parasitics. So you create an inductor, but the parasitics introduce capacitance. You create a capacitor, but the parasitics introduce more capacitances and inductances. So eventually, all of these passives resonate. That's why it is important to understand that and understand the Q and the bandwidth. Why is that important to know both the Q and the bandwidth? Because if you have a system made of components and your matching networks or other passives that you need will be part of those, any Q and bandwidth here in a cascade will impact the Q and the bandwidth of the whole system. So if you start designing without having an understanding of the importance of those, then your system, and you design them individually, you put them together, the system is not going to work. So as we do everything, so now you know, as you do everything in a high frequency amplifier, first of all, there are no lumped elements the way we understand them in low frequencies. Everything is distributed because we make them using traditional fabrication methods, all right? So everything is distributed. The resistors are distributed. The inductors, the capacitors, the higher the frequency you go, the more distributed they are. Everything is distributed. Everything resonates. Everything has a Q and a bandwidth. And so you cannot talk about a receiver without understanding the fundamentals. Now, all of this, they may seem to you as throwing, rocks here and there in a totally random way, but it's not random. And that's what I'm talking about. The system, it brings the pieces together. Now, with that, I would like to go to a homework that I will give you, that I have uploaded, but I will solve a similar problem, yet different, but a similar problem today. So before I start that, do you have any questions? Can you hear me, first of all?
Yes, ma'am.
Okay, because last time we had some problems. Okay, so now let's do the homework, or similar to the homework, I should say. Okay, what you see here is something that we are going to cover in detail later, but here I will give you like a recipe. Still, even if it's a recipe and we have not developed that recipe, a designer is not going to just take somebody else's recipe. A designer is going to create his or her own recipe. However, for us here, the recipe is good. And then later on, we're going to go and learn how to do more complex amplifiers. But for now, we have, in fact, to create an amplifier out of a transistor chip. Somebody gives you a transistor. You write something, Texas Instruments, they send you a transistor. And now this is a transistor, is a chip, has all the characteristics as you will see later. You have all the parasitics in place, but how are you going to make that a low noise amplifier? That's the question. So the theory we are going to have says the following, and look at figure 1. To be able to do out of a chip, this is your chip here, to be able to create an amplifier, low noise or high power, for now it's low noise the way we've done it, you will need to be able to match the amplifier on both sides. Otherwise, you're not going to get the gain you want, and you're not going to get the characteristics, stability, noise, and so forth that you want. In this particular application, we're looking only at the gain, and we are using a recipe to do that. So now, why at this point you're going to appreciate why it is important to use the matrix terminology. Because people who develop, as I said, passives, they talk, system designers, they talk about passives in ABCD kind of language, because it's easy, provides the gain for them. But people who do active device characterization and who use active devices for amplifiers, they use scattering matrix terminology, okay? So,
Could we
yes.
go back to the last diagram?
Yes, this one. So, and then we will find out what will be in this particular, for us to be able to design these matching networks, we'll assume that Z sub G equals to Z sub L equals 50 ohms. Can you hear me?
Yes, I can hear you.
Yes, ma'am.
Okay, okay, perfect. And then you will assume that we are gonna find gamma SM and gamma LM here, should be LM, okay? Now, if I find these two entities for you, these two complex parameters, and I ask you to design the two matching networks, will you be able to do that? Yeah, it's like identical to homework 1. You remember how we did homework 1?
Yes.
Yeah, we were given a complex number that was like, for example, the reflection coefficient, or an input complex load, but the reflection coefficient, all of the reflection coefficients are calculated in terms of 50 ohms. You need to remember that, all right? So as I said before, multiple times. So now the only thing in creating out of this chip and low noise amplifier is to identify the two matching networks and to make them. Okay, what is the process to do that? First of all of active devices are given in scattering parameters. And I will tell you the example that I have for this homework and the example that I will do today. So the homework and the example are using different active devices. For the homework, I found a bipolar transistor, an example that works up to 6 gigahertz. And that I got from Agilent, all right? So here, I believe it's Agilent, yes. So this is the, there are a lot of data, but I wanted to attract your attention to the following. Look how this chip is given to you. It has, of course, incorporated all of the chip package parasitics. So you don't have to worry about how the transistor itself has been put in its own package, all right? Because they are not given to you like in open environment, they're packaged for protection and all other things. They're given to you in terms of the scattering parameters, see? And usually what you have, in this particular case, they will only have the scattering parameters, but you have the frequencies. Now you have here the bias conditions, all right? Now you don't care, they just tell you, you're not gonna develop that for now. You just see the bias conditions. And then for different bias conditions, they give you different frequency ranges or the same, depending. So see, the last one is only going up to 4. So the previous ones go up to 6. So they give you different ranges, frequency ranges, or the same, but then they give you S11, S21, S12, and S22 as a function of your of the magnitude and the phase. All right. Now magnitude and phase. Now, you then, on the basis of your operating frequency, will have to choose from these tables. You know more or less where your operating frequency is. You will have to figure out whether this device can work well. What are the first very early indications that you can easily develop your device? There are these two parameters here. All right, these two, K and D. These two parameters are important because they are helping you to understand how stable that particular transistor that you will select at that particular frequency will be. So these two parameters are called the stability parameters. It's K, so stability parameters. All right. They are K and D. And the earliest test that you have to do before you select your transistor and your frequency will be to make sure that using these general formulas, that your K, for now, has to be above 1 and your magnitude of D below 1. And that will make your transistor unconditionally stable. You know what that means? Have you seen this before? Probably not.
It's always stable no matter what frequency.
And matching, all right? So it will be stable, it's not gonna start oscillating. That's good. Beyond that, if you are not careful with the matching, then an inappropriate matching is gonna lower your gain. That's what is gonna happen, all right? But if you know that these two parameters apply and are in this range, one is above 1, and the magnitude of the other is below 1 of the D, then you know that you don't have a problem with oscillations. Now, of course, there are cases, and we will cover those later, where your K is below 1, and then your transistor has to be matched carefully to be able to be stable. But you can match it, and in fact, if you want very high gain, or if you want very high power, the best designs are the transistors which are conditionally stable, all right? We'll do that later. So there are still ways to match a conditionally stable transistor to make it a good amplifier, especially for high power and for high gain. However, if you wanna do a low noise, a good low noise, decent gain amplifier, and a conditionably stable transistor is the best choice, all right? So now that's where we are. Then, here is the recipe. Then the recipe tells you the following. When your K, all right, you can read the whole thing, it just prepares you for the recipe. But the recipe practically starts here. And that's the important piece. Assuming that you have selected your transistor to have K above 1, usually magnitude of D most of times is less than 1. We don't worry, but I would always calculate it. Then the recipe tells you the following. If you design the two matching networks, so your reflection coefficients, you remember that gamma SN that I showed you above, and the gamma LM, they are here. Gamma SN, gamma SM here, gamma LM here. These two, if I find these two, then I have the matching networks. And these two are given by these formulas, all right? So from, assuming your case above 1, you calculate your D, and then you go upwards. You calculate your C1, C2, then your B1, B2, and then eventually you calculate this. And then when you do that, you have the 2 reflection coefficients, and from there, you can find your matching networks. All right, and then you know that this is gonna give you the maximum available gain that you can get under low noise conditions. And the maximum available gain, as a matter of fact, theoretically, it will have to satisfy this. And it will, if you do the matching networks correctly. All right? Any questions so far before I go to the example? Okay. I will assume that we don't have questions.
Sorry, real fast.
Yes.
You said that was for K greater than 1, right?
Yes.
Okay,
Yes.
thank you.
Okay. Now,
Hold on. I haven't
yes.
finished looking at the equation yet.
Yes. Okay.
Could you please zoom back?
Those are also on eCampus.
Had they been uploaded? Oh, that's homework 5.
Yes, and this is also the theory that we are doing today. Okay, but this, all right?
All right.
Yes. And I will, okay. You see why K has to be above 1? Because in the, in here, there is a square root of K squared minus 1. And the available gain, of course, is in terms of power, so it's a real number. That's why K has to be above 1 to be able to do this unconditional matching. If K is less than 1, then your there is a different, of course, you have to do a different approach to get the gammas. You cannot get the gamma SM and the gamma LM from these functions anymore. You have to go to the Smith chart and do some kind of trial and error to find where they're right, because on the Smith chart, we're gonna learn where the stability regions are for a potentially unstable transistor. We'll be able to draw the stable regions on the Smith chart, and we are going to find an operating point to have the transistor operate in those regions. And that is what we're gonna learn later, but not for now. This is for unconditionally stable. And again, remember, this is a good approach for low noise medium type of gain, which is in fact is this G maximum available of an LNA practically, okay? This is a good approach to design an LNA. We're gonna see those more, but now this is the recipe. I don't want you to know anything more about that, but the only thing we did from here is to find the 2 gammas. And from there, then you go to the design of the matching networks. Okay, so now I will do an example on the basis of that. Let me go back here, and I would like to show you this one. Okay, That's a different BJT. I selected that because I was able, it's also a BJT, and but it's given by NEC. It's a different one. And look at the interesting thing. Very interesting. It has been, the transistor itself has been designed for, I mean, you know, if you want to consider 1 gigahertz high frequency, but very low noise there. And because people will operate it around the lowest noise point, the FT is only 7 gigahertz. You see that? You remember what we called FT? Who will tell me what the FT is from what you remember from the active devices?
You have unity gain.
Unity gain for the intrinsic device, all right? Without the package parasitics. Remember that. There is another one which is called F max. What is the F max?
Unity for extrinsic.
No, it's unity for power, but it depends on the load, correct?
Exactly, and the parasitics, the package parasitics and the whole thing. Usually F max is lower than FT, as you can imagine. But you have to stay, people who are good designers are trying to make F max to be as close to FT as possible, but it's lower. And yet you have to stay away from both of them. In any case, this is what I found. I liked it because there are a lot of them, a lot of data sheets that are available from industry. And this one I liked. I skipped all of this and I went directly to the scattering parameters. Here are my scattering parameters. Okay. And let me see whether I have highlighted. There are all kinds of the scattering parameters. Okay, so if I remember well, the ones that I selected, which I'm going to write down, it's for operation at 5 gigahertz, and I'll show you where I was. 2, 3, 6, 3,000, 5,000. Okay, I went at 5.779. Okay, here, I'll show you which ones I selected. The interesting thing about this, and you can ask me why I selected that. I selected it at 5. It's close to my, this particular one has, of course, it's a higher frequency design. It is close to my frequency, close to 5G. But look at what also I paid attention. The nice thing about that, it has K also calculated and has the maximum available gain calculated. So if you do it correctly, I'm gonna get this high of a K. So K will be 1.23. And then I will have like a nice maximum available gain of 7.5 dBs, which is nice if you think that I will have relatively low noise. Now the noise is not calculated here, but you can calculate the noise. We will see how to calculate the noise later. All right, so I selected those. So what do you do in a case like that? Let me get, just a second. So my lecture notes here on the right. Okay, so now I'm going here. What I did is exactly, I wrote down what I have. Okay, my S11 is practically 0.779, 157.4. My S21 see is S21 first. S21 is 1.135, and then it's 32. S12, which then comes next, is point
Excuse me? Is
yes.
this an unequal sign, not equal sign for S21?
I'm sorry, it was like a thing that was generated from that. 0.385 minus 100.4, and then S22, 1. Well, let me see. No, is S11, S21, S12. Yeah, this is S22. Okay, S22, and then S12 is here. 103. $53.2. Okay, then what you do is practically what I would do myself is to confirm that your K from the K formulas that you have seen, and K, according to the formula here that I showed you before, K is a function of K is given as from the S parameters plus D. So you have to calculate D, which is S11, S22 minus S12, S21. And then from there, go and calculate, and that has to be less than 1. And then you have to go to K and confirm that your K, if it's available by the manufacturer, confirm that you got this value. K is 1.23. 1.23. Then after you do this, you calculate the formulas. You calculate C1, you calculate C1, which is practically, you plug in the values for S11 minus D, S22 complex conjugate. In this particular case, I found my D to be 0.438. So, it's, in my case, so D was 0.438 for me. I have made also some rounding, all right, to make those calculations easier. And then you find C1 and C2. From C1 and C2, you go and calculate B1 and B2. And B1 and B2 are real numbers. So practically, if I were to go back for a moment and look at, let me go back. Look at this, all right? So what you're gonna have is D, you saw before. It's a complex number. C1 and C2 are complex numbers, but B1 and B2 are real numbers, as you can see. And then from B1 and B2, you go into the expressions for gamma SM and gamma LM. And here you will see the following. Here you will see that the numerator is real and has two possible, all right, values, B1 plus B1 squared minus 4 C1 squared. So it's a real number divided by 2 C1. So your gamma SM has a phase which is the negative of the phase of C1. Unless this number here, so, and that if, that is true if B1 squared is larger than 4 C1 squared, okay? However, if B1 squared is less than 4 C1 squared, then your numerator becomes B1 plus J of this. Okay, so it has there is also a complex number in the numerator. And then, of course, in this case, the case below that I have here, in this particular case, your phase for gamma SM, the phase for that, is going to be different, of course, than the phase of C1, all right? Because you're going to have a J in the numerator, and C1 is also a complex number. Now, the other thing you have to pay attention to is that in addition to plus, I will have a minus. So practically the minus is going to give me, if in the second case, it's going to give me that. And of course, in the first case, it's going to give me a different number in the front, on the top, right, if they're both real. But you are going to have two solutions. Now, if some of these solutions, if one of these solutions gives you gamma SM magnitude to be larger than 1, you're going to dismiss it. And you're going to take the other solution, because if one is larger than 1, the other is going to be smaller than 1. So the red one, for example. So gamma SM will be less than 1. So the one of the two solutions that is giving you gamma SM larger than 1, you're going to always dismiss it, because we're not going to have reflection coefficients that is larger than 1. What does that really mean? It means that you have reflected power out of your network, which is more than the incident. And it's like your network has another source, all right, which is not, we don't want to do that. It's not, we don't want to have this. So it's only the solutions from here, from this, you're going to select only the solutions that give gamma SM less than 1 and gamma LM less than 1. Okay? So that's where you're going to stop after you calculate. So now let's go to my other notes. Now, after you have calculated from all of this, your gamma SM your gamma SM and your gamma LM in magnitude and phase, they're going to look like this. This is going to be magnitude, which is going to be less than 1, e to the j phi SM. And this is going to be magnitude, e to the j phi LM. Okay? And of course, in your solutions, I will again remind you, this will have to be less than 1. Now, it is true that all of your solutions could be less than 1, which means that all of the solutions are possible, all right? It's not always true that one of the magnitudes in one of those solutions is going to be higher than 1. But if it's higher, you dismiss it. If it's not higher, you keep all of them, and all of them will give you different matching networks who can do the job equally well, all right, in terms of matching the amplifier. Now, from all of those, some will be better than others when you start thinking about the Q or the resonant frequency or the bandwidth of your matching network, all right? Because so far, so good, you've done this. Now, the next challenge is to find the matching networks. In this, of course, homework, or for our project, the projects, you know, they are open-end, so I'm not going to tell you where to stop. In the homework, obviously, I'm not interested in you going only for every solution you find, all right? Just pick one of your gammas and then try to realize that. I don't want to tell you that if you find 2 solutions for one and 2 solutions for the other, I want you to go and create 4 possible combinations. No, select. So you're going to select one solution for gamma SM. You're going to select also one solution for gamma LM, and you will try to develop those matching networks. In reality, though, if I am an engineer and I have to provide the best possible amplifier, that means that my matching networks should not take away any of the power. Because if my matching networks have long lines and they're too big, then I will have losses, metal losses. I will have dielectric losses. Plus I will have long lines will have inductances. Narrow lines will give me high metal losses, as we discussed. So there are all of these other considerations that come into play that eventually will make out of these possible solutions only one to be the best. But I don't want you to do this for the homework. For the homework, just select one and go with that. Now, we have practically, we don't have any more time, but I would say that process took us exactly where we were at homework 1, okay? And so that is going to also, what I'm going to do next time is to start with these kinds of reflection, desired reflection, and I will do it for my own example. And then I will show you how I would match, this amplifier, what kind of matching network I would then create to for this amplifier, and how I will be thinking when I'm creating this matching network. But that's what we're going to do it on Wednesday. For today, I want you to remember what I told you very early about the things that are important for you to remember, all right? Transmission lines and matching networks, network theory, ABCD, and scattering matrices and the whole thing, and resonators. Very important components that we need to put together. So together is the first time when we try to we start to integrate those concepts in ways that are also related to our systems. In any case, with that, I would like to ask if you have any specific questions. If you do, please join me through the office hour, during the office hours. And let me see if there are any questions.
I have a question.
Yes.
The syllabus says that we're having our midterm Wednesday, September 30th. I believe that's Wednesday of next week. Are you planning on doing that?
Yes, and it's gonna be on the material that we are gonna cover. So of course, it's gonna be something you're gonna have for 15 minutes. It's gonna be like a take-home kind of exam. I will make it available to you in the beginning of the hour. Then you're gonna have to submit it at the end of the hour. And it's going to be on the material we have covered so far. All right, transmission lines and matching networks, some network and matching networks. Yeah, some network theory on some things on resonators. But it's not gonna be different from the things that we have done. Practically, it's gonna be a small variation from the things that we have done. It's not gonna be anything new.
Okay.
Also, I have a okay, go ahead.
You just said take-home format. Does that mean it's open notes, open
Yes,
book? What do you mean?
exactly. It's open everything. It's open everything.
Does that have time restriction?
It has what?
Time restriction.
Yes, I mean, it's going to be designed so you can finish it in during the duration of the lecture. So it's not going to be a long, thing, as you can imagine.
Would you be okay with giving, like, say, another 10 minutes at the end to allow for scanning and submission?
Yeah, I will. But I know that some students may have a class. So practically what I would, I will make it short. It's going to be a relatively short. You cannot do a design of anything during that. But I need to make it in a way that you can finish it and do also the scanning for the upload, obviously.
Okay, thank you for clarifying that.
Sure.
Professor,
Yes.
do you think it would be possible to would we be doing a review on Monday for exam midterm material? What going over what would be on the test? Like a quick overview what would be on the test? If that makes sense.
Can you hear me? Can you hear me? Can you hear me now? I don't know what the other thing was. Maybe it was because of the weather or something they have. Okay, tell me. Yes. You were saying something, but I did not hear it because there was a lot of noise here.
Oh, okay. I was wondering, do you think maybe on Monday it would be possible if we did like a midterm review,
Yes.
going over,
You know what I would suggest, because Monday, obviously, I would like to do it over the weekend, because on Monday it's Yom Kippur, and the people, it's a celebration for a number of people, and so the weekend is gonna be the review, so everybody can make it.
Oh, okay, got you. I must
Okay.
have missed that part. Sorry about that.
No problem. No, I think, and I will let you know on Wednesday the times.
Okay, awesome. That sounds great. Thank you.
Sure. Okay, so I will see you at 3.